Chapter 9.2 Centripetal Force 1. Centripetal Force. An object in uniform circular motion has a constant speed but changing velocity, so it is accelerating. The acceleration is given by v squared over r. The force that produces such acceleration is called centripetal force. As centripetal force always points towards the center of the circular path, the centripetal force must also point to the center of the circular path as well. When you roll a mass, the tension exerted on the mass pulls the mass towards the center. In other words, the tension provides the centripetal force. As centripetal force is always perpendicular to the velocity of the mass in motion, the force cannot speed up or slow down the mass. Centripetal force can only change the direction of the motion. So, centripetal force does no work done on the mass, and the kinetic energy of the mass is not changed by the centripetal force. In this chapter, you will see many examples of circular motion, and find out the source of centripetal force in different cases. For example, a dish of food on the turntable is performing circular motion. It is friction on the dish that provides the centripetal force. Example 3. Centripetal force. A piece of bread performs circular motion inside a microwave oven. The centripetal force acting on the bread comes from the friction by the turntable. Try checkpoint 3 on the next page. Two. Verifying equation of centripetal force. This part explains an experiment to verify the equation of centripetal force. F equals mv squared over r equals mr omega squared. Therefore, to check the relationship between force F and angular velocity omega, and also that between force F and radius r. The situation as in checkpoint 3 is not common, in which the strain is horizontal. On the other hand, when we vary a mass, the strain is not horizontal, it forms a conical pendulum. The mass is at a point by only two forces. The net force is the horizontal component of the tension, and it provides the centripetal force for the circular motion. Therefore, if the equation of centripetal force is correct, we should have, in the horizontal direction, T sine theta equals mr omega squared, and so T equals m omega squared L, which is equation star here. And so in the experiment, we will measure T and L to check if they are directly proportional. And we will also measure the angular velocity omega to see if F is directly proportional to omega squared. By the way, how to check if Y is directly proportional to X?
We will make a centripetal force apparatus using the materials shown. Measure the mass of the screw nuts and the rubber bung with an electronic balance. Connect the screw nuts and the rubber bung with a piece of nylon string. Set the distance L between the rubber bung and the glass tube to 1 meter. Mark the length with a paper marker. Whirl the rubber bung horizontally. Remember to keep the paper marker just below the glass tube. Record the total time needed for 50 revolutions and calculate the angular velocity of the rubber bung and the tension in the string. Repeat the experiment with different lengths. Does the equation for the centripetal force hold for different values of L?
As you can see in the video, that the angle theta here is always changing when we roll a mass. So it is impossible to measure that angle theta during the experiment. By the way, how can we improve the accuracy of measuring the angular velocity, omega? 3. Centripetal force and Newton's first law of motion. Take a look of the following experiment and see what happens when centripetal force is not supplied.
There are a thin layer of small beads and a particle circular rail in a tray. Place a ball against the rail. Strike the ball to make it move along a circular path. What will happen when the ball leaves the rail? Watch the motion again from the other angle. When the ball leaves the rail, the normal reaction acting on the ball by the rail disappears. As a result, the ball moves in a straight line due to inertia.
When the ball is given a push, it rolls along the circular rail. The normal reaction by the rail on the ball directs to the center of the circular rail. Such normal reaction provides the centripetal force for the circular motion. When the ball rolls to the end of the rail, the ball leaves the rail. Since then, there's no more normal reaction S on the ball. The ball experiences no net force, and so it travels in straight line afterwards. Similarly, when we roll a mass, and if the string suddenly breaks, the mass will fly off along the tangent to the path. Example 4. Verifying the equation of centripetal force. This example gives you some very important hints for doing the experiment. Read carefully. Do check point 4 on the next page.